Some words in mathematics are dangerous. In this video, the dangerous word is certainty, because mathematics feels like the place where certainty should live. A proof is not an opinion. A theorem is not a guess. 2 plus 2 does not depend on mood, fashion, or authority. Mathematics seems to promise something rare, knowledge that cannot be shaken. But in the early 20th century, mathematicians began to ask a disturbing question. Can mathematics prove that its own methods are safe? Not just, can we prove this theorem? But, can we prove that proof itself will never betray us? That was the dream behind David Hilbert's program. To understand why that dream mattered, we have to see the pressure building around mathematics. The 19th century had been extraordinarily successful. New geometries had appeared. Calculus had become more rigorous. Set theory opened a new world of infinities. Algebra, topology, and analysis were growing in power. But success brought danger. The more abstract mathematics became, the more its foundations seemed to need protection. If geometry could change its axioms, what made a mathematical system legitimate? If infinity could be treated as an object, what rules controlled it? If sets could contain other sets, could they contain themselves? Then came paradoxes. Russell's paradox shook the foundations of set theory and logic. Frege's attempt to build arithmetic from logic was damaged just as it neared completion. The old confidence was no longer enough. Mathematics needed foundations. Some mathematicians wanted to restrict mathematics to what could be constructed directly. Others wanted logic to provide the ground. Hilbert chose another path. He did not want to give up the powerful mathematics of infinity. He did not want to abandon classical reasoning. He wanted to secure it. His idea was bold. Treat mathematics itself as a formal system. Write down axioms. Write down rules of inference. Turn proof into manipulation of symbols. Then step outside the system and prove something about it, that it cannot lead to contradiction. This is the heart of Hilbert's program. Mathematics would become formal. Proofs would become objects of mathematical study. And consistency would be proved by methods so concrete and finite that no one could doubt them. This was not a small technical project. It was a new level of mathematics. Mathematics would study mathematics. Proof would become the subject of proof. This field came to be called Metamathematics. The dream had several parts. First, formalize mathematics. Second, show that the formal system is consistent. Third, ideally, show that mathematical questions can be decided by systematic methods. The deepest hope was security. No hidden contradiction. No paradox waiting inside the foundations. No theorem and its negation both provable from the same rules. Because if contradiction entered the system, certainty would collapse. A contradictory system is not merely inconvenient. In ordinary logic, once contradiction is allowed, the system can prove far too much. Proof loses its power to separate truth from falsehood. So consistency was essential. Hilbert wanted a guarantee. A proof that the machinery of proof could not explode. But certainty has more than one meaning. A system might be consistent. It never proves both a statement and its negation. A system might be complete. Every statement in its language can be proved or disproved. A system might be decidable. There is a mechanical procedure that always gives the answer. These are different dreams. Hilbert's larger program was surrounded by all of them. Consistency, completeness, decidability, formal security. Together, they formed the hope that mathematics could become a perfectly controlled structure. This hope did not come from naivety. It came from the power of axioms. Euclid had shown that geometry could be built from assumptions. Hilbert himself had rebuilt geometry with modern axiomatic precision. If geometry could be made exact, perhaps all of mathematics could be made exact. If every proof could be reduced to symbol manipulation, perhaps mathematics could be checked from the outside. A proof would no longer rely on intuition. It would be a finite object. Line after line. rule after rule, every step inspectable. This is why Hilbert's program was so attractive. It promised to save the infinite by controlling it with the finite. Then came Kurt Gödel. In 1931, Gödel published his incompleteness theorems. They did not say that mathematics is meaningless. They did not say that proof is useless. They did not say that truth is a matter of opinion. They said something much sharper. Any consistent formal system that is effectively axiomatized and strong enough to express arithmetic has limits. There will be arithmetical statements that the system can neither prove nor disprove. The system cannot be both complete and consistent. This was the first incompleteness theorem. The idea was startling. Gödel found a way for arithmetic to talk about proof. Numbers could encode symbols. Symbols could encode formulas. Formulas could encode proofs. A statement about numbers could become, indirectly, a statement about whether a proof exists. Then Gödel constructed a sentence that, in effect, says, "This sentence is not provable in this system." If the system proved it, the system would be inconsistent. But if the system is consistent, it cannot prove it. So the sentence is not provable inside the system. And yet, from outside the system, if we trust the system's consistency, we can see why the sentence is true. The system cannot capture all arithmetical truth. This was not a trick of language. It was not the old liar paradox simply moved into mathematics. It was a precise arithmetical construction inside formal proof. The second incompleteness theorem went even deeper. A sufficiently strong consistent system cannot prove its own consistency, not by its own resources. This struck directly at Hilbert's hope. Hilbert wanted secure formal systems whose consistency could be proved by safe mathematical means. Gödel showed that the strongest version of that dream could not work. The system could not climb inside itself and certify that it would never contradict itself. This is the point where certainty changed. Mathematics did not collapse. But one kind of certainty became impossible. The dream of a complete, self-certifying formal foundation for all mathematics could not survive. There would always be a gap between system and truth, between proof inside the rules and understanding from outside the rules. This is why the word certainty is dangerous. It sounds absolute. But in mathematics, certainty depends on the framework. A theorem can be certain relative to axioms. A proof can be mechanically checkable. A formal system can be powerful and consistent. But no sufficiently strong system can give every guarantee Hilbert wanted from within itself. Gödel did not end Hilbert's influence. In fact, Hilbert's program helped create the very tools that made Gödel's theorem possible. Formal systems, proof theory, metamathematics, the study of syntax, the idea that proofs themselves can be encoded and analyzed. After Gödel, proof theory did not disappear. It changed. Mathematicians continued to study consistency. They studied relative consistency. They studied stronger and weaker systems. They studied computability, models, and formal verification. Later, Alan Turing and Alonzo Church showed that no general algorithm can decide every mathematical question of the kind Hilbert had hoped to mechanize. The dream of total decidability also met a boundary. But boundaries are not failures in mathematics. They are information. Just as non-Euclidean geometry showed that Euclid was not the only possible geometry, Gödel showed that formal proof was not the whole of mathematical truth. Just as topology changed what same meant, Gödel and Hilbert changed what certain meant. Certainty did not vanish. It became more precise. A proof is still one of the strongest forms of knowledge humans have. But proof lives inside systems. And systems have limits. That is the structure behind the theorem. Hilbert wanted to protect mathematics by making proof completely formal. Gödel showed that formal systems powerful enough for arithmetic cannot fully protect themselves. The lesson is not that mathematics is broken. The lesson is that mathematics is deeper than any single formal cage. Axioms matter. Rules matter. Proof matters. Consistency matters. But so does the space around the system, the metamathematical view from which we study what the system can and cannot do. Mathematics wanted absolute certainty. It found something more subtle. Not the end of proof. The limits of proof. Not the collapse of foundations. The beginning of modern foundations. And behind that shift was one of the most profound realizations in mathematical history. To understand mathematics, mathematics had to turn its own methods back on itself. For more stories behind the ideas that shaped mathematics, subscribe to Behind the Theorem.